So let's talk about ROS2 based. ROS2 means Robot Operating System. ROS2 based navigation and simulation stack for the Robotino. Three authors: Saurav Bose, Tariq Beeman, Alexander Ferin, and Gerhard Lakemeyer. First of all, what is the main objective of this paper? So the main objective of this paper is to operate Robotino using ROS2 and simulation. Simulation means, simulation means virtual robot movement, right? So developing a system, that means developing a system where the simulation as well as the real robot will work same way. Previously, there was ROS1 support was there previously, but officially no ROS2 support was there. So that's why these researchers, they are preparing a new navigation stack based on ROS2. What do you mean by Robotino? Robotino is a mobile robot manufactured by Festo Didactic. Mainly, this Robotino is used in universities, robotics research centers, automation industry 4.0, digital twin, warehouse automation, logistics, etc. So the main job of this Robotino is the main use will be working in teaching as well as conducting research also. Coming to the hardware side of this Robotino, uh, coming to the hardware side, normally mobile robot will be moving forward and backward, right? Okay, but in this Robotino, that is having holonomic drive. I will write here holonomic drive. So normally the mobile robot will move forward and backward. But in this case, this Robotino can move forward, backward, left side, right side, etc. And also this can move 360-degree like this, either clockwise direction as well as in the anti-clockwise direction. We call it as holonomic drive. Then first point is the holonomic drive. Okay. And the second point is this Robotino is having infrared sensors, close range infrared sensors. So that means around this Robotino, it is having different sensors, infrared sensors. Using these infrared sensors, the Robotino will be able to identify different obstacles, collisions, etc. Next is IMU, Inertial Measurement Unit, IMU. Okay, so I have mentioned the Robotino can move forward, backward, right side direction, left side direction, clockwise rotation, anti-clockwise rotation, right? So how much degree this Robotino rotate? Okay, or what will be the speed of this Robotino? What will be the speed of this robot? All those details will be measured with the help of this IMU, Inertial Measurement Unit. So this Robotino, where we can use this Robotino? First one is for navigation. So Robotino will identify its path and it will be moving through that particular path. Then the second one will be the mapping. Robotino will develop the map of the entire room where this Robotino is located. Office mail delivery. So we can use this Robotino to share mails from one room to another room. Then RoboCup logistics leak. In factory simulation, we have, raw materials, right? So we have to transfer the raw material to the machine, right? And once the machine will process those raw material, next will be the assembly and then finished goods, right? So in between the sections, the Robotino will play a major role to transfer box from one location to another. So previously, the old Robotino used Ubuntu 18.04 or 20.04. So programming options was C++, REST API, Robotino View, ROS1. So the problem was ROS1. Now this ROS1 is an old technology, right? So during the time they are preparing this paper, it's the time to end the support of ROS1. So the next standard will be ROS2, right? So the new technology will be ROS2. So we have to transfer this to ROS2. Why ROS2 is better than ROS1? So fast communication, better security than ROS1, multi-robot support, DDS communication, better performance, real-time support, lifecycle nodes, multi-threading. So now this ROS2 is a new technology and ROS1 is old technology right now. Okay, so one is ROS2 and then next is NAV2. So what is nav2? Nav2 means it's a navigation package. This is the navigation framework of ROS2. So this navigation to package or this nav2 package will decide how to reach the destination, how to avoid the obstacle, which path is suitable, okay, where we want to go, right? Now where is the correct location? So all these informations will be managed by this nav2. So nav2 is a navigation framework of this robot operating system 2. So as I have mentioned, the first one is localization. So localization means robot don't know where is the correct location, right? But this navigation package, using this navigation package, localization was possible. And then second one is mapping. Okay, mapping will create the entire map, the map of the entire home. And then the third one is path planning. It will find the shortest path from say point A to point B. That is what is called a path planning. And then the next one is obstacle avoidance. Okay, if the robot will see an obstacle, it will go in another path. Then goal navigation. So goal navigation means, suppose now the robot is here, the goal is to reach point B. Goal navigation means this is the point given by the user, right? So there is a goal to reach here. This navigation is what is called a goal navigation. So this nav2 will do all these things: localization, mapping, path planning, obstacle avoidance, and goal navigation. Okay, so in this paper, they have these researchers, they have prepared ROS2 navigation. Okay, so inside this ROS2 navigation, localization, mapping, then navigation, simulation, everything will work inside this ROS2 navigation. For the simulation environment, they have used an application called a VBoats simulator. I will write here VBoats simulator. VBoat simulator. So in this VBoats simulator, they have prepared the virtual Robotino, and inside that they have added LiDAR, IMU. IMU means inertial measurement unit, wheel, motor, sensors. All the informations they have added into this. Okay, first of all, what do you mean by LiDAR? So LiDAR means light detection and ranging. So LiDAR means using laser. Okay, it will calculate the distance. Okay, using this LiDAR, this will calculate the distance. What will be the distance from the objects? Okay, then based on that, it will prepare the map of the room. So in this paper, now we have virtual robot, right? And then we have a real robot. So both robots will do same task. So what was the task? Inside the warehouse, box transport, right? Box transport. Box transport, navigation, obstacle avoidance, localization. Then hardware driver. They have used ROS2 hardware driver developed by Grips team. And they have run a program inside the simulation, and they have run that same program inside the real robot. So the simulation result was, so we have a virtual robot, right? Then we have a real robot, right? So they have prepared a program and then run that program in this simulation. Okay. And the same program they have run in the real robot also. So the result was, so the simulation result was same. So from that, we can say, this ROS2 navigation stack is working suitably with Robotino. So what are the main contributions from this paper? So in this paper, these researchers, they have developed ROS2 for Robotino. They have developed V-boat simulation environment. LiDAR-based navigation they have prepared. Using navigation 2, now to implemented autonomous navigation, and they have compared results between the simulation robot as well as the real robot. Using the ROS2 hardware driver, they have conducted experiments in real Robotino. And the result was both these two scenarios, that means in the simulation as well as the real robot, the Robotino is showing same performance. So this paper is directly related to the Robotino digital twin, because whatever topics mentioned in this paper was directly related to me. That means ROS2 navigation to V-boat simulation, Robotino platform, LiDAR localization, mapping, path planning, autonomous navigation, simulation, etc. So coming to the ROS components overview. Okay, so in this paper, they are managing the Robotino using this ROS2 and NAV2, right? Using this ROS2, this is showing the components overview of this ROS. Here we have different colors, right? We have uh, pink color, we have green color, white, etc., right? We will see one by one. So the complete architecture will be, we have LiDAR, right? Then we have laser scan integrator. Okay, then we have map server, right? Then AMCL, then planner server, right? Controller server, right? Velocity smoother, right? Robotino driver, robot motors. So this LiDAR, we can say this will be the eye of the robot. So this will be scanning 360-degree. This LiDAR will be, if, for example, if there is an obstacle, the LiDAR will be identifying that obstacle and it will be measuring how much distance that obstacle from this mobile robot. So this LiDAR will scan 360-degree. So the output will be laser scan. Then whatever data coming out from the LiDAR, on those scan data will be combined into the navigation system. This is what is called a laser scan integrator, right? So this will be like a scan filter. So the output will be scan. Then a map server will be this will store the map. For example, if we have a factory map, right? Storage, press, assembly, CNC, charging station. So when the robot is moving, it will be using that map. Then AMCL means adaptive Monte Carlo localization. This will be used to identify where is the current position of the robot. Localization. AMCL means adaptive Monte Carlo localization. Then we have a behavior server, right? So during the time of navigation, what the robot will do during the time of the navigation. For example, if there's an obstacle in front of the robot, back up or rotate or continue. Okay, so what will be the next step? If so, what will be the behavior during the navigation time? That is what is called a behavior server. Then we have another one called planner server. Planner server means, so for example, it's like a planning. This is to identify the shortest path. For example, the Robotino in the current position right now. Okay, the goal is to identify the best path to reach the location B from A to B. So planner server will be finding the shortest path. Then we have controller server. Okay, so based on the planner server, now the shortest path is identified, right? So the controller during uh, the message coming out from the planner, right? Okay, based on the planner server, the robot will move from the current position to the required position. For example, sometimes it will be a straight line path or left or right stop. So controller will be converting that information into wheel speed. Velocity smoother. Okay, just imagine if the robot is changing the speed very quickly. Okay, right now the robot is moving like this. If the robot will changing its speed very quickly, what will happen? Jerking will happen, jerky motion will happen, right? So this velocity smoother will slowly increase the velocity, right? So that it will give a smooth motion. For example, starting from 0, 0.1, 0.2, 0.3, like that. Otherwise, this will produce a jerky motion. That is what is called a velocity smooth. Then coming to the Robotino driver. So Robotino driver means now we have software, right? We have this robot, right? So the Robotino driver, the interface between the software and the robot is what is called a Robotino driver. Okay, say for example, the planner will be saying forward. Okay, then the Robotino driver motor controller, based on that the robot will move it. Same way encoder data driver rosto. Then we have another one is called a joy node. Joy node means using joystick. Okay, if we use joystick to operate the robot, we can use this joy node. That means in manual mode, right? So using joy mode, it will be connected to the Robotino driver. Then static transform. So robot will store all the position of sensors. For example, base link, laser, camera, IMU, the distance, rotation, all the data will be stored as TF. Then TF publisher. Transform frame. This is the main part of ROS. This will be telling the relations between coordinate frames. For example, we have map, odom, base link, laser, camera. So how this nav 2 is identifying where is the current position of the robot using TF. So finally, we have LiDAR, right? Then laser scan integrator, then map server, then AMCL, planner server, controller server, velocity smoother, Robotino driver, finally go to the Robotino robot wheels. So when the robot sent the sensor data to encoder, Robotino driver, odometry, AMC, using the joystick, joy node, Robotino driver to the robot. This joy node is for manual drive. So So in this paper, they have developed ROS2 based navigation system. They have developed a ROS2 based navigation system for Robotino. So using this, we can run the Robotino using the same ROS2 code. We can run the simulation robot as well as the real robot, or means virtual. We can simulate virtual robot and real robot using the same ROS2 code. So the main objective will be rapid prototyping. We can develop navigation algorithms very fastly. First, we can run this code in the virtual Robotino, and then after that we can do the same code to the real robot. In this way, we can reduce the development cost, and also we can compare the performance between the real robot as well as the virtual robot. For that, they have used a simulation framework called a VBoot simulation framework. So this figure 1 we have already discussed. This is explaining the complete overview of ROS2 software architecture. All the software, how all the software components are connected. So this is showing, this is the software component side, right? How all the software components are connected. This picture is showing how all the software components are connected. Initially, the operating system used in Robotino was Ubuntu 18.04, Ubuntu 20.04. So they have upgraded this Ubuntu 20.04 to 22.04 because this ROS2 LTS, that means ROS2 long-time support Humble will be working very smoothly in Ubuntu 22.04. That is very important. This ROS2 long-term support Humble. So this will be working in Ubuntu 22.04. Okay, then what is ROS2 Humble? ROS2 Humble means ROS2 long-time support version is what is called a Humble Hawksbill. This is a stable version as well as long-time support. LTS means long-time support. ROS2 LTS. LTS means long-time support. What are the main packages they have installed? One is REC RPC, remote procedure call. This is to communicate. We have different software services, right? In order to communicate different software services, they have used remote procedure call package. Then Robotino TEV. These are the files required to develop Robotino application, includes libraries, header files, etc. Robotino API 2. This is a very important package. This was given by a C++ API. Using this, we can control the Robotino hardware directly. We can control as well as read using C++ because of this Robotino API. Robotino Diamonds. This is background service. This will be giving the main service. RPC, the remote communication service. Control D3, robot motion control service. Gyroscope service. Robotino driver is working based on these services. Then Robotino 4 hardware extension. Normally, in the Robotino having infrared sensors, but researchers, they have added SICK TIM571 LiDAR sensors. So why LiDAR sensor is, they have added LiDAR sensor? Because infrared sensor, these sensors, they will be detecting small distance only. But if we have very large distance, for example 360 degree scanning, more accuracy, we need LiDAR. Because of LiDAR, the navigation will be more. 3D printed mounts. In order to place the LiDAR, there is no mount in the Robotino. Because of that, they have manufactured a mount using the 3D printing technology. So this is showing in figure number 2. So in this figure, it is showing that this 3D printed, this mount was manufactured using 3D printing technology. The core component of this system, I have already mentioned. This picture is showing the software component side. So the core component of this entire system was Robotino driver. So this Robotino driver, this will be the interface between the ROS2 as well as the real robot hardware. So what is the duty of this Robotino driver? Drive kinematics. That means, for example, the forward motion, rotate, right, left. Okay, what about the movement of the Robotino? This will be managed by this drive kinematics. Odometry. Odometry means how much distance this robot covered in X position, Y position, heading. How much distance this robot covered. CMD well topic. So in ROS2, to move the robot, we will be using a command called CMDVEL. For example, linear velocity 0.5 meter per second, angular velocity 0.2 radian per second. So Robotino driver will be changing this to motor speed. CMDVEL. We have two sources, right? One is joystick, CMDVEL, Robotino driver. Another from Nav2, navigation goal, planner, controller, CMDVEL, Robotino driver. So CMDVEL, inverse kinematics, wheel 1 speed, wheel 2 speed, and wheel 3 speed. We have built-in sensors. So driver will be managing gyroscope, how much distance the Robotino turned, right? Of infrared sensors, obstacle detection, bumpers. What is the use of bumper? Say, for example, if the Robotino hit some objects or not. So all these sensor data will be published as ROS topic. For example, gyro, IR, bumper, etc. Static transform. So each sensor from the robot base frame, right now where? So the driver will be publishing this. For example, base link, laser, IMU, infrared, joint state. Driver is also publishing another topic, joint states. What is the current position of the wheel? What about the wheel rotation, wheel velocity? Using this odometry, localization, navigation, everything will be working. External LiDAR is already connected. SIP TIM571 LiDAR. With the help of this, all the ROS topic, we can publish the data. For example, scan front, scan rear. So this laser scan data we can use in AMCL, localization, SLAM, mapping nav to planner, obstacle avoidance. So in this page, they have mentioned about, so they are using Ubuntu 22.04 plus ROS2 Humble, and using the central interface Robotino driver, and using the code CMD well, they have properly controlled the Robotino, gyroscope, infrared bumper, wheel encoder, lidar. Using this reboots simulation plus the real robot, using the same navigation stack. They have developed a platform using the same navigation stack, and this navigation stack we can use in real robot as well as the virtual robot. Because of this plan, the development was very faster, and the experimental cost was reduced, and also we can compare the performance between the robot in simulation as well as in real environment. We can compare the performance. Okay, so now we have two images, right? So this image is showing the robot. The robot, this is the real robot, right? The real mobile robot, whereas this is showing the simulation robot. Okay. And for simulation, they have used application called VBots, VBots simulation. And in the real robot, they have placed two lidar, right? Okay, one is in the front, right, and another one is in the back. So these two are the two lidars they have added. So because of this lidar, the Robotino will be able to locate its environment 360-degree very accurately. In simulation also, they have used the same lidar. Because of that, whatever laser scan data will be getting in the simulation, it will be very much close to the data from the laser scan data from the real robot. So we have LiDAR, right? Okay. And using the ROS2, they have used the official ROS driver package provided by the SICK company. So for the Robotino, there is no ROS2 driver. That's why they have used. Developed by Grips team, RoboCup Logistics League. So this team developed ROS2 driver. So they have used this driver. So this driver will be communicating with the hardware using Robotino API 2. So the working will be like this. So ROS2, then Grips driver, and then Robotino API 2, and then robot hardware. This is the working. So the main advantage of this was in the simulation as well as the real robot will be working same. This is the main concept mentioned in this paper. Also, we have two LiDARs. One is in the front and another one is in the back. Front LiDAR and rear LiDAR. So combining these two scan data, preparing a common topic. Okay, we have front scan and a rear scan combined into a common topic. This is what is called a laser scan integration that we have mentioned right previously, right? Yeah, here. So here we have a front scan and a rear scan. Then combining these two scan data and into a common topic called a scan. This is what is called a laser scan integration. So because of this, robot will get information in front of the robot as well as the rear side of the robot. Extended Kalman filter, EKF. EKF. This is the main algorithm mentioned in this paper. In order to identify where is the current position of the robot, they will be using different sensor data. They have used a wheel encoder, that means odometry, and then IMU, gyroscope. So these two informations will be combined, this odometry as well as the EMU combined, so that we will be getting the accurate position of the robot. For that, they are using EKF, extended Kalman filter. So if we will use only odometry, okay, because of the wheel slip or some small errors, some position drift will happen. Similarly, if we use IMU only, If time increases, drift also will increase. So we have to combine odometry plus IMU so that we will get accurate position of the robot. Localization. So based on the position given by extended Kalman filter EKF, AMCL localization, we can locate where is the current position of the robot in the map. So now the current position of the robot is here, just imagine. After doing the localization, nav 2 will current position, goal, path planning, obstacle avoidance, navigation. So they have used 3 mobile robots for experiments. And the experimental area was RoboCup Logistics Lake. So the experiment was conducted in simulation, so the factory environment in simulation as well as in the real factory. So in the simulation, how the robot traveled, okay? Similarly, what about the real robot? Whether the real robot traveled in the same way mentioned in the simulation. Okay, so comparing these two results, whether in simulation as well as real robot, we will, in this paper they are saying that they will get uh, similar results. Because of that, their ROS2 integration was successful. Related work. So they have mentioned previous researchers, Pitonakova. They have compared Gazebo, VRUP, Argos. They used 3 different softwares. They checked the speed, CPU usage, memory, and real-time performance. For big environments, Gazebo is very much useful. But for small environment, in order to manage uh, multiple robots, Argos is good. Then Shamshiri et al. They have compared VBots, Gazebo, Argos, VRUP, basically for agricultural robotics. They have checked the ROS to support physics engine, robot library, sensor library performance. Their finding was VRUP was suitable based on their requirement. Simeon Dis. So these researchers, they have compared different robot simulators. They have studied Gazebo and VBots. These two simulation applications getting large community support, also good documentation. Because of that, these two are using commonly in robotics research. So there are different simulators. So researchers, they are using different robotic simulation softwares. One is Gazebo. So the main advantage of Gazebo is that it is having good interoperability between rows two. And another advantage is that having a very huge robotics community. But the problem was visual realism. And also it requires more CPU, GPU, computational overhead. Another one is called VBots. VBots. So the advantages was rendering. Using GPU, rendering will become very much faster, and the robot library, uh, having a large amount of robot library, and also integration with ROS2 for research as well as educational purpose. This VPORT is very much useful. Domain randomization is one of the major challenge. Environment customization. When we compare with the Gazebo or Copelia Sim, comparing with these two, environment customization was very less. Another one is called AIR Sim and Carla. This is mainly for these are the simulators. AIR Sim Carla mainly for autonomous vehicles. The advantages was very realistic 3D graphics, high quality visual realism, huge amount of 3D asset library. The disadvantage was needs powerful computers. CPU, GPU usage was very high. Copelia Sim, more than multiple physics engines, Python, Lua, C++, MATLAB, different interfaces was there. Very useful simulation environment. Why they have selected VBots? So the main objective of this paper was integration with the ROS2, right? Interoperability. Okay, because of that, they have selected VBots because ROS2 bridge was available, Robotino model was available. We can simulate very quickly, and also we can experiment navigation algorithms very quickly. Zwilling et al. So these researchers, they have used Gazebo and they have developed Robotino simulation. And they have connected the referee box of RoboCup Logistics Lake. And the disadvantage was they didn't use the ROS2, they have used a Fox framework, Abdo et al. This research was basically related with visual odometry. Visual odometry means using camera. Using camera, how much distance the robot will travel. That technology is what is called visual odometry. They have conducted in a Robotino Sim professional MATLAB and also with the real Robotino. Using visual odometry, they have conducted the localization very successfully. Nizamuddin. This team also they have used visual odometry, but navigation system, NI LabVIEW, first one navigation software. These two applications they have used. Extreme ambient light, camera will not work properly. Dynamic obstacles. If the object is having the same color similar to the environment, the camera will not be able to identify the object. So using only this visual odometry is not at all a good idea because of this disadvantage. Then Biskov et al. They have used hierarchical reinforcement learning. The concept was they have divided big navigation task into small movement primitives. For example, the goal will be go straight, turn left, avoid obstacle, reach goal, right? So because of that, planning will improve, dynamic obstacle avoidance will improve, real-time navigation will become possible. Then VBot's Robotino driver. This is the main technological contribution. The main objective was we have Robotino in VBoot simulator, right? So connecting that Robotino to ROS2. So for that, they have used VBoot's Robotino model. So inside the VBoots, they have prepared the Robotino model. So they have used the Robotino model previously prepared in VBoots. In that, having wheels, motors, sensors, robot body, everything was there. ROS2 bridge, VBoots ROS2. They have used this ROS package. So ROS2 is communicating with VBoots, and also VBoots is communicating with ROS2. So for example, ROS command velocity, then VBoots robot will move. Or LiDAR data with the ROS topic. So the Robotino driver will be the main part of this system. Robotino driver will receiving the velocity command. CMD velocity. So topic will publish, for example, linear velocity 0.5 meter per second, angular velocity 0.2 radians per second. Kinematic model. See, the Robotino is having 3 omni wheels, right? So using the kinematic model. Using the wheel encoder data, identify where is the current position of the robot. X position, Y position, heading. So we have 2 robots, right? We have simulation robot in VBoots, right? And we have a real robot, right? So the simulation robot will behave exactly like the real robot. And the simulation robot is exactly imitating the real robot's behavior. So in this paper, they have used VBoots because of the interoperability with the ROS2. Then to connect this Robotino with the VBoots, they have used VBoots ROS2 bridge and developed the central structure of Robotino driver they have developed. This driver will collect information from ROS2. So for example, command velocity, and it will be converted into the 3 omni wheels motor commands. Wheel encoder, IMU, LiDAR, all these sensor informations published as ROS topics and calculated the odometry. So through this simulation, plus real Robotino is working with the same ROS2 navigation stack. So they have developed a centralized platform. They have developed a centralized platform where this system can be used in simulation environment as well as the real environment. So next is drive kinematics. So the Robotino is having three wheels, right? Three omni wheels, right? Okay. So using these three omni wheels, this Robotino, we can move this Robotino in front, back, left, right, etc. So in this image, you can see world frame, right? This is the world coordinate system. For example, factory map, warehouse map, room map, etc. So right now, where is the current position of the Robotino using this world coordinate system? So for example, we have a factory, right? Or we have a room. Okay, and the room is having X, this is XW, and this is YW. Okay. So based on this, where is the current position of the robot? Then we have robot frame. Okay, world frame, then robot frame. So this is the coordinate system of the robot. So for example, if the robot is changing, okay, for example, if the robot is turning 360-degree, this coordinate system also change. So this XR, this XR will be in the front side. Then coming to the wheel position, we have three wheels, wheel 1, 2, and 3, right? And these three wheels are three omni wheels, right? And every wheel is having one position and one angle. Okay, if you take this wheel, it is having position. Position means radius as well as angle. So in this paper, you can see this distance is RA, this is RB, and this distance is RC. That means from the robot center to the wheel, this distance is mentioned RA, RB, and RC. Then delta A, delta B, and delta C, this is the orientation angle. Okay, so wheel 1 0 degree, wheel 2 120 degree, wheel 3 240 degree. See, in differential drive robot, the robot will be moving forward, backward, and rotate, right? This is what is called a differential drive robot. Differential drive robot. Differential drive robot. Okay. But in Robotino, the advantage is that this is omnidirectional, right? Omnidirectional motion. That means this can move forward, backward, right, left, right, rotation, any direction. This can move. Omnidirectional. So this is not a differential drive robot. Next is kinematic model. The mathematical model, for example, this direction. Okay, which direction the robot is want to move? For either forward direction or backward direction. Okay, Then what about we have three different wheels, right? One, two, three, right? Okay. So how much speed this wheel should rotate? And the mathematical model that is used to find all those is what is called a kinematic model. C. This is what is called a motion command. C is equal to Vx, Vy, omega. Vx means linear velocity in x direction. Okay. And V, for example, 0.5 meter per second, Vy 0.3 meter per second, y direction, and omega means angular velocity. That means the rotation, radian per second. So for example, Vx 0, Vy 0, omega 0, or Vx 0.5, Vy 0, omega 0, like that. Okay. So if you give Vx is equal to 0.5, Vy is equal to 0, omega is equal to 0, what will happen? The robot will move like this, right? And if you give Vy is equal to 0.5, the robot will move sideways, right? Like that. And if you give 0, 0, omega 1, okay, so here the robot will rotate like this. Okay, but if you give Vx equal to 0.4, Vy is equal to 0.3, omega is equal to 0.5. Okay, so this will move forward as well as sideways rotation, both three. Then we have one equation. Okay, Vx, Vy, omega, right? This Vx, Vy, omega, I have already mentioned. Okay, x direction, y direction, omega means rotation. Converted to kinematic metrics. So converted to kinematic metrics. Omega m1, omega m2, omega m3. Okay, so this will be converted to, so this is the motion command, right? So this motion command will be converted to what? Converted to the wheel speed. Converted to the wheel speed. So these three represents the RPM of the three wheels. Okay, say 120 RPM, 180 RPM, 90 RPM, etc. K is what is called the uh, kinematic matrix. Wheel position into wheel orientation. Using wheel position and wheel orientation, that matrix is what is called a kinematic matrix. Then R represents the wheel radius. If the wheel is very small, then we need more RPM. If the wheel is big, we need small RPM, right? And then we have a 60 by 2 pi, right? So in ROS using meter per second, right? So converting velocity into RPM, we will be using 60 by 2 pi. Then gearbox ratio. In robot, having motor and wheel, right? So there is a gearbox. So they have used a gear ratio of 16 is to 1. Gear ratio 16 is to 1 means if the motor will rotate 16 times, wheel will rotate 1 time. Okay, so if the motor rotates 16 times, the wheel rotate 1 time. So because of that, this will be getting more torque, 16. So the gear ratio is 16:1. So as the motor rotates 16 times, wheel rotate 1 time. And scaling factor. In simulation, we don't have a real motor, we don't have a real gearbox. Because of that, in simulation, the robot will move very quickly or slowly. For that, they have used a scaling factor SSC 0.009375. Why this scaling factor is required? In simulation, 1 meter per second. Okay, but in real robot, it is 0.7 meter per second. So in that case, using the scaling factor, we can change the speed. Why they have used the scaling factor? Because the robot in simulation as well as the real robot should behave in a similar manner. That's why they have identified an empirical scaling factor. Okay, in this page we have discussed about forward kinematics, right? Forward kinematics, right? Next is inverse kinematics. So in forward kinematics, we have used command velocity Vx, Vy, omega, right? Then kinematic model, then wheel RPM, then motor. This is what is called a forward kinematics. Okay. Next is called the inverse kinematics. Inverse kinematics means now the robot is moving. Okay. So now the robot is moving means the robot knows the wheel speed, but they don't know how much speed, how much rotation, sideways, how much distance. So we have to find all those things is what is called the inverse kinematics. In this motors in Robotino, every motor there will be an incremental encoder. So encoder will measure how much time this motor rotated. Okay, and also how much, what about the speed? For example, wheel 1. Okay, so we have wheel 1, say 120 RPM. Wheel 2, 118 RPM. Wheel 3, 125 RPM. So the encoder will measure all those things. So now the robot is moving, right? So the wheel is moving. So encoder will measure this data. Okay, so from this we will get the motor speed. Then from there we will get wheel angular velocity, inverse kinematics, we will get the robot velocity. Then we have another equation here, equation number 2, write this one. Then omega, MA, MB and MC. K inverse represents the inverse kinematic matrix. Vx, Vy and omega. So this omega A, omega B, omega C represents the angular velocity of the three wheels. So using this equation, we can find how much distance the robot traveled, how much distance in sideways, how much rotation it will take. From the image, you can see we have three wheels, right? So these three wheels, and this is the robot center, right? And these three wheels are at same distance from the robot center. That means RA is equal to RB is equal to RC. And the wheel orientation 60 degree, wheel A 60 degree, wheel B 180 degree, and wheel C 300 degree. This is the standard configuration of the Robotino. Then coming to the odometry. This is main part of ROS navigation. Okay, suppose the Robotino is moving, right? Okay, now where is this Robotino? How much distance? How much distance this robot covered, right? How much rotation it will take? We can find all those data using encoder. So the encoder will identify all those details, right? Wheel speed, inverse kinematics, and robot velocity. Say for example, let's take a delta t time, a small time. How much distance it traveled. Then incremental position. Delta x, delta y, delta theta. For example, say for example, the robot moves forward, say a small distance, right? Say say delta x is equal to 0.1 second. Time. Okay, so 0.1 second time the robot traveled. 0.1 second. I will write 0.1 second. So delta x will be 5 centimeter, delta y is equal to 0. So previous position was say 2.5 and 1.8. So the new position will be old position plus increment, that will give you the new position, right? So 2.5 plus 0.05 will be 2.55. So TM is what is called a transformation matrix. So as I have already mentioned, we have a world frame and we have a robot frame, right? So transforming this robot frame into the world frame is what is called a transformation matrix. So we have equation number 3. So the new position is equal to old position plus the rotation matrix, then into velocity into delta t. How much time? Delta t means the time interval. If the encoder data is correct, then odometer is also correct. In simulation, one of the major problems they have observed was in ground, the wheel will slip, right? The same effect they will see in the simulation also. That means in real robot, no slippage, but slippage was happened in the simulation. Then time discretization. Simulation is calculated in every step, right? This is not a continuous motion. So because of that, there will be a small error. So because of that, the simulation odometry plus real odometry, when we compare, both are different. So because of this problem, they have added a GPS sensor in simulation. So this GPS sensor will give the correct position than the encoder odometer. So because of that, the wheel slip time discretization, these type of errors happened in the simulation, we can avoid. So that we will get a proper odometry comparing with the real problem. So previously they are saying that during the simulation, odometry was not correct, right? Because of wheel slip as well as time discretization error. So because of that, they have added one GPS sensor, GPS. In V-boot simulation, they have added one virtual GPS sensor. So this GPS sensor will give the correct position of the robot. So when they have conducted a simulation, they have used GPS-based odometry. In the Robotino, it is having some built-in sensors, right? Infrared sensors, IM initial inertial measurement unit. Other than these two sensors, they have added SICK LMS 291 LiDAR. So using the LiDAR, we can improve the navigation, localization, we can create the map of the environment, find obstacles, identify walls in front of the robot, V-Boots sensor plugin. In V-Boots, to use sensor having special plugin already available. So when we run the simulation, so LiDAR data will published in ROS topic. For example, V-Boots laser scanner scan, V-Boots ROS2 driver. So this V-Boots ROS2 driver will be communicating between vboots and ROS2. Static transform. So ROS should know where is the exact location of each and every sensor. For that, baselink laser IMU infrared publishing this transform control. This is the real part to move the robot, right? ACT thread. This is a special thread in Robotino driver. They are calling as ACT thread. This will be working in regular intervals, 50 Hz or 100 Hz, etc. Command velocity message. Navigation stack or joystick will send a command to the robot. For example, Vx 0.4, Vy 0, Omega 0. So the driver will receive these commands and based on the kinematic equation, calculate the wheel speed. So once the robot is moving using a particular command, after moving the robot, the command driver will delete that particular command. If new command is not coming, the robot will immediately stop. This is a safety feature. In this paper, they are saying that the driver thread frequency will be equal to controller published frequency. For example, the planar frequency will be 20 Hz and the driver should be 20 Hz. Otherwise, the motion will not become smooth. Localization and navigation. Now the robot is ready. Sensors, driver odometry. Next stage will be robot will identify its path and move automatically. For that, ROS2 ecosystem they have used, existing packages they have used. They didn't write any new softwares. They used ROS2 Nav2 stack. AMCL means adaptive Monte Carlo localization to locate where is the current position of the robot in the map. Okay, we have LiDAR, we have map, and using AMCL, where is the current pose of the robot. So AMCL is basically used for differential drive robot, but Robotino is an omnidirectional robot, holonomic robot, right? So the motion model changed so that we can use in Robotino. The main problem was wheel odometry was not correct. Because of that, IMU was added. Sensor fusion. So we have two sensors, right? Wheel encoder, IMU. So plus we should use EKF. Now itself the sensor fusion package is available in ROS2 robot localization package. They have used EKF for EKF mode. Output odom filtered. This is the odometry with more accuracy. To start the navigation in ROS2, they have used nav to bring up. In this, they are getting planner, controller, recovery, behavior, everything different. What they have tuned? Their main focus was on path planning and path following. They have improved. Because in factory navigation, the path planning is very important. So planner. Okay, what is the duty of planner? Okay, now this is the current position of the robot. The goal is to reach point B. Okay, we should find which path is the correct path, which path is the suitable path to reach point B from point A. So for example, right now the robot is in the storage area, right? Next is should reach to press station, right? So the planner will find the suitable path to reach the pressing station from the storage. Planner server. So there is a node named planner server in nav2 having two inputs. Goal location. Goal location means where this robot should go. For example, 5.2 or 8.4. Which algorithm should use? Planner plugin. In nav2, having three different planner plugins. Nav FN planner. This is the old planner. This was using DIJ KSTRI algorithm. A simple, reliable, trustable. The disadvantage was the path is having more turnings. Then another one is called SMAC Planner 2D. This is based on hybrid A star. It is more smooth plan, faster planning, and good optimization. Theta star planner. Mentioning this planner was the best planner. Theta star is equal to A star search into line of sight. A star search will identify the shortest path. Line of sight. If the robot can go in a straight line, it will avoid unwanted turnings. Because of that, the theta star will uh, reduce the zigzag, will give direct path, less time, small distance. So the suitable path for Robotino was theta star planner. So now FN will follow more grids, path will be more turnings will be there. Okay, as you can see. But SMACA planner is more smoother than now FN, but theta star will be less turnings. And in the paper, they are saying that this is the best one. Okay, starting point. For example, this is the starting point and this is the goal. Okay, straight come from here to here and then go. This is the direct path. So the planner will give the path only, right? So the duty of the controller is to move the robot through that particular path. So planner will give you the path. So for example, in this image, the planner will give you the path, but the controller will give the wheel speed so that the robot will move. Then controller server. This is the low-level motion controller. The job is to follow the robot path. Nav2 default controller. In Nav2, normally using DWB controller. DWB controller means dynamic window-based controller. Okay, so at the same time, the robot will be moving forward, backward, left. Which one is good? Okay, this will check. So this dynamic window-based controller will check which one is suitable. This is actually a reactive controller. That means this will be checking the obstacle in front right now. It will not predict the future. Right now, what is the obstacle in front of the robot? So in warehouses, we have more than we have multiple robots, right? So obstacle will be changing. So this DWB is not able to handle those situations, so that they have used another controller called MPPI, Model Predictive Path Integral. This is model predictive control based controller. Okay, that means next to 1 second, 2 second, 3 second, previously calculated. Okay, next to 1 second, how the robot should move. Next 2 second, 3 second. Okay, so for example, if the robot is moving, okay, in front of the robot, another robot is coming. Okay, so the robot will think, if I move forward, collision will happen. So take a sideways and move. So the difference between DWB and MPPI. So DWB is reactive. It will check the existing situation only. Constant action. Static environment is better. Simple, less computation. But MBPI is predictive. It will predict the future. Dynamic optimization. For dynamic environment, MBPI is best. More intelligent than DWB. More more computation. So they have selected MBPI. So the Robotino is using in factories, warehouses, RoboCup logistic leaks. So in those situations, having other robots, human beings, boxes, dynamic obstacles. So the best controller will be MPPA. So the advantages of MPPA was predictive control, future will predicting, dynamic model, trajectory optimization. It will be checking multiple path, and then based on that, it will select the right path. Dynamic obstacle avoidance. Even though the obstacle is moving, it will create a new path. So in order to work this MBPI controller, we need to adjust different parameters. This was mentioned in this table. Time steps 80. So this means the future 80 time steps the robot will predict. Model DT 0.05 seconds. So every prediction there will be a time limit. There will be a waiting time, right? That means 0.05 seconds. That means 50 millisecond. That means delay time. Frequency 20 hertz. Every 1 second, controller will give new command. Motion model. Motion model is omni because the robot is an omnidirectional robot. Batch size 2000. That means each cycle it will be checking 2000 possible trajectories. Vx minimum minus 0.7 meter per second. This is the maximum distance, sorry, maximum velocity. It can move in the backward direction. Then Vx max 0.7, that means in the forward direction, the maximum distance. Vy max 0.7, sideways distance. That omega z means the maximum rotation, 0.8 radians per second. Vx std, this is the standard deviation of the forward velocity sampling. Vy standard deviation of sideways velocity sampling, and omega z angular velocity sampling standard deviation. So time step is equal to 80. Time step is equal to 80 means it will predict in 80 different small sections how the robot will move in future. So model DT 0.05 seconds means each prediction having an interval of 0.05 seconds. So the total prediction time will be 80 into 0.054 seconds. So that means using this MBPI, approximately 4-second time is required to predict the motion of the robot. Frequency 20 Hz. Every second, the controller will send new commands 20 times. Motion model Omni. This is not a differential drive robot, right? This will be moving in forward, backward, sideways, diagonal rotation. So that's why this is called omnidirectional robot. Because of that, we should select Omni motion model. Batch size 2000 means every controller cycle checking 2000 different trajectories. Then, based on the 2000 different trajectories, select the appropriate one. Best trajectory, choose the best trajectory. So this was one of the major advantage of this MBPA. Velocity limits. We have velocity limits, forward, backward, sideways, rotation. Now evaluation. So they have conducted their system. For that, they have used an environment 6 meter into 12 meter factory. This is the factory simulation field. This will be exactly similar to the RoboCup logistics lake. In the environment having border walls, static machines, mobile Robotino, these machines we have treated as obstacles. The task of the robot, okay, gave 5 random paths. Every path having 4 waypoints, start waypoint 1, 2, and 3. So robot should reach these 4 waypoints in this order. So how this random point selected? The random point selected where the points very nearer to the machines. This is to replicate the exact factory navigation. Every experiment they have repeated 5 times because to check the consistency. ROS to bag recording. Every experiment ROS they have recorded ROS to bag. In ROS to bag, CMD velocity scan odometry TF IMU goalposts. Experiment 1 E1. In experiment 1 they have used one Robotino and they have conducted experiment in 2 different situations. One is V-boot simulation and a real robot. Experiment 2 they have used 3 robots simultaneously, multi-robot scenario. As per the table 2, simulation real robot execution time ratio will be 1.01. That means the real robot will be more than 1%. So this ratio represents the simulation will be exactly mimicking the behavior of the actual robot. Also comparing the path, the travel path in simulation as well as the real robot. In some places, we have sharp curves in simulation, but in a real robot, this will be taking smooth trajectory because of the wheel slippage. In simulation, this is not mimicking the correct wheel physics. So that's why the sharp curves developed. So, so this table is showing the different experiments E1, E1 sim, E1 R1, E2 sim R1, E2 R2, E2 sim R2, E2 R3, E2 sim R3. So E1 means using only one Robotino and comparing P-boot simulation and a real Robotino. Experiment 2, E2. E2 means they have used three robots, R1, R2 and R3. They have operated three robots simultaneously. And each robot, they have considered the other robot as dynamic obstacles. And based on that, they have do the navigation. So E1 represents real robot. E1 simulation means this is the simulation robot. Then E2 R1 real robot 1. Then E2 simulation R1. This is simulation robot 1. Then E2 R real robot 2. E2 sim R2 simulation robot 2. E2 R3 real robot 3. E2 simulation R3 simulation robot 3. P1, P2, P3, P4, P5. These are the 5 navigation path. So each path they have repeated 5 times. And the time will be showing here. Average execution time. Path 1, 45.45. Simulation, 51.36 seconds. So delta represents the variation, consistency. If the delta is very less, that represents the robot is moving perfectly. If delta is more, that represents every run time is changing. In experiment 1 robot, in the simulation as well as the real robot, the execution time is approximately same. But in simulation, the robot will be taking sharp curve, but in a real robot, it will be very smooth because of the pose estimation error wheel slip. And another problem they have observed was turning behavior. Sometimes the robot will be turning as well as producing a forward motion simultaneously. Because of that, small side movements happened in real robots. Experiment 2, they have used 3 robots. This is the more practical experiment. That means 3 robots moved at the same time. And every robot is considering other robot as dynamic obstacle. Based on the simulation, the real robot will be 16% slow because of the recovery behaviors. Odometry error. In simulation, they have used a GPS-based odometry, but in real robot used encoder and IMU. So the position estimate was not accurate. Static obstacles. In simulation, the machine position was 100% accurate, but real factory a small position change was there, so that also affected the navigation. Semi-transparent obstacles. So some objects the laser scanner will not be able to identify. So sensor reading was not that good. That also triggered the recovery. So this figure number 6 is showing the path of the robot. Okay, 6A, B, and C. Experiment 1, path 1, right? Then 6B, experiment 1, path 2, 6C, trial 2, path 3. In this paper, they are saying that experiment 2, run 2 was not good because collision recovery behavior, slow navigation was happened. So, what are the outcomes from this? So, they have conducted two navigations. One is single robot navigation, and the next one is multi robot navigation. In single robot navigation, the difference was only 1%, comparing the simulation as well as the real. But in multi robot, the difference was 16% more because the wrong information based on the wheel encoder odometry. In simulation, they have used GPS based localization, and the real factory machine position, there are some small deviations, right? And another problem was very difficult to locate transparent objects. Okay, so in this research, they have prepared a ROS2 based complete navigation system for Festo Robotino. So they have developed a complete ROS2 navigation system for Festo Robotino. They have used two LiDAR sensors to locate to see the environment, right, 360-degree environment, and also to find the exact position based on the map and autonomous movement to the uh, required position. For localization, they have used the nav2 framework in ROS2. So localization means it is used to identify the location of the robot. To do the localization, LiDAR, EKF, AMCL they have used. They have developed a navigation system to move from one location to another location. They have used a theta star planner MPPI controller. In this simulation, they have used V-Boots simulation. Here, they are prepared the environment simulation, mimicking the exact size of the robot, sensors, movements, factory layout, etc. And finally, they have compared the simulation plus the real robot results. Okay, so totally they have used 3 robots. The navigation result we got in simulation, it will be approximately same because they don't have any dynamic obstacles. and they will get results in simulation as well as real robot exactly similar. But in the simulation, uh, they have find the wheel slip, okay, but only in simulation. But in real Robotino was not there. So that represents the simulation physics was not correct. Improve more the simulation physics. So the future work was custom recovery behavior. They are planning to develop an intelligent recovery algorithm, cost map. So they will avoid the region where obstacle was there, and they will select a new safe path, IR sensor. Okay. Still, the Robotino is having a more number of infrared sensors, and the LiDAR is using. By improving the infrared sensors, the obstacle detection will be improved. Bumper sensor, if the Robotino will hit to some object, it will activate the bumper sensor. Using this, we can reduce the collision damage, and also we can increase the recovery. Multi-agent pathfinding, MAPF. The algorithm used to work multiple robots without collision. So using this, this will find the best path without collision. This is very important in multi-agent pathfinding.